GM, everyone. Ismael from Lagrange here. I'm joined by Michael from Fabric Cryptography.
Hey everyone, GM.
Thank you for being here, Michael.
Thank you for hosting me.
We're in Bangkok right now.
Yes.
Con.
Yes.
There's a question I like to start with often to ask people. Have you taken the motorbike?
Yes.
Ha! And I love how decisive you were in that answer.
Yes.
And your experience was positive or negative?
It depends on whether your experience with a roller coaster is positive or negative, or I could actually answer the same for like my experience in the semiconductor industry. You have your highs and you have your lows, and it's a thrill, and at the same time, it's life-threatening. So, yeah.
For the sake of the future of zero-knowledge proving systems being accelerated on hardware,
Yes.
I would hope you stop taking those bikes.
Yeah, I've stopped.
Perfect. I'm sure the your investors watching will be very happy to hear that.
Completely stopped. I did it 3 times.
Okay.
The first time I was like scared out of my mind. Cars narrowly missed my arm and things like that.
Yeah.
And then the second time I was like, okay, I already know this is the devil I know, so I tried it again and I was like, that was pretty okay. And then the third time there was like a nasty turn.
Oh.
And I was like, okay, I'm never gonna, because the fact that the experience replayed itself from the first time made me think this is pretty dangerous, actually.
The thrill of doing it wears off, and then you realize it's just bad idea.
Yeah, it's a terrible idea.
Yeah. It just becomes dangerous and no longer exciting.
And sometimes they don't have the helmet.
Exactly. And this has been a very interesting week because a bunch of the areas that you guys touch with the VPU are incredibly prominent in the conversation of the conference.
Yes.
From ZK to TEs to FHE.
Yes.
Is this your first DevCon? What has the discourse surrounding all of this been like for you?
Oh, that's a great question. This is our first DevCon actually being really substantively a part of the conversation. Like we went to DevConnect in Istanbul last year, and that was like completely different. You know, over there, it was like I barely had panels or talks, and I was just like entering the space as a chip guy, and that was a very different vibe. This time, I think there's a really deep appreciation on everyone's part for what hardware can bring to the table, and that's incredibly encouraging to see, because I think there have been some conceptions of hardware in the crypto community that are well-intentioned for decentralization and things like that, but ultimately, hardware is this incredible force for decentralization, and I think that's what people are finding.
Hardware is an incredible force for decentralization.
Yes.
I actually haven't heard that mentioned by anyone else previously. I'm being honest. I'd love to know a little bit more what you mean by that.
Yeah. It's funny because if you look at Bitmain, that's what most people think of hardware in crypto. And it's a really unfortunate comparison because Bitmain was a massive force for centralization. Like you have 5 Bitcoin pools, you have 20 major Bitcoin miners, and that's it. And you only have 2 manufacturers, and it's Bitmain and MicroBT.
Yes.
Right? Like, this is not the kind of image of hardware that would be ideal, right?
Yeah.
But then if you look at history, hardware is an incredible force for decentralization, right? Like the amount of compute that you have in your pocket today was in the realm of the very, very few, in literally non-existent in 1945, right? Like you didn't have stuff like this. And then at first vacuum tubes were used by governments and national institutions, right? And universities, and then they became the domain of companies, right? Like companies could have them. And then Moore's Law brought it to every pocket and brought something that's more powerful than a Cray supercomputer to every pocket. And so that is the democratization that we're talking about. That is the decentralization we're talking about. And now the countries in, for example, Africa can receive billions of smart devices.
Exactly.
And so if you look at Kenya, like now, Kenya's going digitally native with its cash system, M-Pesa.
Yeah.
And that is a transformation that only occurred because of silicon acceleration.
Yes.
Right? And so that is what I'm talking about. You have the power to print these things. I always say every chip is a shard of the future printed a billion times. And that's what we believe chips can be.
That's very well put. And so in essence, competitive private markets around performant hardware have driven down the cost of that and democratized access to compute on a global scale.
Exactly.
That's fascinating.
And
I love how you put that.
Over and over again. Like now, if you look at ChatGPT, powered by Moore's Law, right? that is now bringing the power of AI inference to
Mhm.
billions of people
Yes.
who didn't have it before. Now, OpenAI, Microsoft, this is a very centralized kind of supply chain.
Yes.
But in the next 10 years, I would predict that the same forces that brought compute to every pocket will bring those supercomputers to every pocket.
Bring into every pocket.
You're going to have inference chips in your phone actually capable of a lot of the same stuff that you see in the AI models that only run in the cloud today and are super expensive. And it's going to happen in ZK. It's going to happen in FHE. It's going to happen in cryptography. And it doesn't have to look like Bitmain.
I like that. I think while we do see a supply chain concentration on the creation of GPUs and on a lot of application-specific chips, the nature of how those chips are dispersed into everyday devices democratizes access to the computational resources.
Exactly.
Despite the fact that the supply chain is concentrated.
Exactly.
That's interesting. And I talk to a lot of people in crypto. Almost everyone in crypto is a software guy. But we started in this conversation today with you calling yourself a chip guy.
Yes.
What does that mean? And how did your background make you a chip guy?
Oh, boy. I never intended to be a chip guy at all. Like, I never for a million years thought that I would be a chip guy. I grew up as the kid of 2 parents who were PhDs in sociology. But they were Chinese tiger parents in America. So they were like, okay, Michael, you're going to study math. Because I grew up at the intersection of those two things, right? On the one hand, my dad had these books that were like piled up to here with grant money. Like he would get like giant boxes of them shipped in on a regular basis. And so I would read about like everything, world history, Chinese history, military history, the history of technology. Right? Like he had a book on everything in society, right? And on the other hand, I studied math, right? And that was like a totally different discipline. And I always found it fascinating how the interplay of forces happened in society. You have like technology shaping culture and culture kind of shaping societal values, and then those values shaping the technology that we build. And like this like cycle was really interesting to me. And so fundamentally, I always wanted to do something that was big, quote unquote, in impact, but didn't know what it would be, right? Like I thought maybe it'll be fusion reactors or something. And then in high school, I was a math kid. So I entered the Olympiad circuit, won the USA Math Olympiad, was a finalist in the USA Computing Olympiad, and did a bunch of stuff like that. And I realized that just doing crazier amounts of number theory didn't seem to me like it was heading anywhere with impact. Now, ironic that we're sitting here accelerating number theory now. But back then I thought, okay, like this is it for me. Okay, this is as much math as I'm excited to learn. Like now I want to turn my attention to things that really scale, right? So fun story, I was at math camp and there is a guy who was a speaker at math camp. And the question I asked him was unlike everyone else, right? So I raised my hand. I was like, how do you get girls, Vlad? And
I love that.
And he was like, I get the table at the club. And I was like, okay, I'm going to study this, right? So I went back home and I was like, okay, I'm going to rethink my priorities and I'm going to start an online business, right? So I went online and attempted to register a PayPal, got banned from PayPal for my entire life. To this day, I think I can't use PayPal because they associate you and join you across everywhere you move and all that. Their anti-fraud engine is really spectacular. And so I can't use PayPal. I can't get a bank account. I am the unbanked.
You are the unbanked.
And fortunately, in 2011, Bitcoin had already come out, so I discovered it. And as 15, I was like, okay, like I'm going to download this thing. I'm going to like totally get into this because it is the only, like I saw that it was really powerful, but this is the only thing in the internet that will allow me to send and receive money. That was like a powerful idea to me. And I got into hardware, finally getting to your question, because of Bitcoin. Actually, because I started investing in GPU mining all across the world in 2012. And then in late 2012, there was an ASIC mining operation that came out of Shenzhen. It was called ASIC Miner. Very boring name.
Yes.
And I was like, ASIC, what's that? And so I invested and I made a killing because for some reason this guy didn't rug. And we actually don't know what happened to this guy. He's called Fried Cat. If you look him up online, he might be dead. Gangs might have killed him. Who knows? Wow. It's really unfortunate because he's an upstanding guy. He actually paid out on this ASIC project, right? That he could have totally scammed everyone. I invested in that and the tape out happened and the chips came back and it was on 130 nanometer. ironically, what we're talking about with open source TEEs now, 130 nanometer. And I remember 10 machines on a table were able to basically be a third of the entire Bitcoin network.
Wow.
And this was the moment where I realized this is what hardware is like.
Yes.
Hardware can deliver this. It's one thing to talk about 10x's and see it intellectually on a page.
Yep.
It's another thing to see it play out. And,
Exactly.
oh, you can actually have something that much faster.
Exactly.
Right? And then over the next few years, of course, we saw NVIDIA do the same thing to AI. And so I was just like incredibly compelled by this, right? So I started going deeper and deeper into hardware, eventually took over the supply chain of a Bitcoin mining company. So I bought a bunch of systems from these guys, right? And then we wound up signing a deal where they just gave me the chips and I built the systems myself because on one hand, that was cheaper. And on the other hand, it looked like the systems weren't going to get delivered on time. And I really was impatient.
Yeah.
And so wound up mounting the systems myself, hiring contract manufacturers at the age of 17. And this was my first entry into hardware. So I went from being an investor to like deeper and deeper down the rabbit hole. And then for a while, I was like tired of hardware because I was like, even this level of hardware was like pretty miserable.
Yes.
So went to MIT, dropped out, started a software company, sold it to Google, small acquisition, and I discovered I don't want to do SaaS. So I went back into hardware with Luminous Computing, which is this photonic AI supercomputer. At first, I was just the software guy.
Yes.
I was supposed to be responsible for the compiler, for the TensorFlow and PyTorch integration, and things like that. And then, unfortunately, we found out that there were system-level issues with the chip. We found out that, actually, AI involves an incredible amount of data movement. And so even if you have this energy-efficient matrix vector multiplication core, that's not going to get you the boost that you want end-to-end. And so this was my first exposure to the importance of end-to-end. And I was like, oh my God, that's a thing. And discovering these issues wound up also putting me down a rabbit hole. So I had to study device physics, basically how these photonic devices actually modulate light. And then, oh shit, they're analog devices. So now I have to study control systems. And then how those control systems work is feedback analog circuits. So I had to discover analog mixed signal circuits and then got into digital because sometimes you need to actually do other stuff with the data that's nonlinear. And so light is not good at it. So got really deep into all areas of chip design. And I'm not a professional, right? Like I dropped out at the age of 19, but what this really taught me was it gave me this really unique lens on knowing 20% of the subject matter across a very wide variety of fields. So if you want me to talk about spintronics or ferroelectrics or things like that, like now I can. And so this is like kind of the experience that brought me to Fabric.
Yeah.
And so how Fabric was founded was basically we were at Luminous and there was a small company called Facebook. You might have heard of it. That came to us and they were like, hey, we want your computers for ads.
Yes.
And this was 2021. Ads were unfortunately the dominant opportunity for AI chips. And I'm not that excited about that. Like I built this 1000x AI architecture. Am I going to use it for ads now? It's like a waste, right? And so I was like, what about LLMs? And they were like, we don't want to buy those.
Yes.
And then the board and the other founders and the team were like, there's no demand for LLMs right now. Like ads are where it's at. So I was like, okay, screw this. I quit. Went home, thought about my life with Tina, and basically Tina was like, this technology that we're doing, it's just making this machine, this system faster and faster, but we're not actually, where are we going? We're making ads faster now? Like,
exactly. Better targeting.
Exactly. And she was like, Michael, I challenge you to come up with a deep tech idea that could actually do something for humanity. And not through some indirect means like inspiring people or whatever, but like actually directly. And oh man, that's a hard one.
It is.
Because when you really think about it, like even if we could produce a vast amount of food, like for cheaper, even that would still run into all
Supply
sorts
chains,
of hurdles.
a whole bunch of issues.
Exactly.
Yeah.
And fundamentally, would it make its way to the countries that need it the most? Probably not. And so it was like, I really had to think about this. And then what came out was like, okay, human trust is at the root of everything, and it's getting worse and worse, right? If you look at societies as they become bigger and bigger, there's like less trust among people.
Yes.
There's more of this like fragmentation of society, right?
Specifically with digital.
Yeah,
It's
exactly.
very hard to establish trust in the digital world.
Digital world, especially with like deepfakes and AI and like, all these new things, right?
Yeah.
And how do we turn back the clock and actually restore trust in society? This is how we decided to make ZK hardware and cryptography hardware.
Interesting.
It actually didn't come from, hey, I think there's this market opportunity for ZK hardware. In fact, if it came from that, we wouldn't ever have done ZK hardware.
Yeah.
It was 2 months after SBF. And the space was like very nascent and there were hardly any rollups, even in testnet.
Yes.
It was like, what are we doing? But we were like, we're going to get started here with rollups because we were like, this is on the way to this grand vision of doing what NVIDIA did for AI, but for cryptography, for really making it ubiquitous, for making it radically cheap, radically fast, and for making that the engine for spreading it into every system in the world.
Yeah. I think that is such a great directional bet when you made it. And I like the fact that you made that bet not simply for the economic outcome it creates, but because of a principle that you felt was directionally correct in society. And I think that's rare when you see companies that are founded on a story like that and not just on pursuing a financial outcome. And so one of the things I've always found very fascinating about our conversations is how when we look at ZK hardware companies in crypto, there's really a plurality of what people are doing. There's people who are using CUDA to try to make proving backend faster on commodity GPUs. And then there's a couple people making ASICs, and some of those companies seem to be disappearing, like some of the early Bitcoin mining ASIC producers. And then there is Fabric, and you're the only company that I'm aware of that's really gone to first principles to design a chip from the ground up with an architecture, an ISA, and a whole design that's more performant for its intended purpose of verifiable computing of a variety of types. So I'd love to know a little bit more about why you took such a deep approach there and why that's going to pay benefits over time.
Yep, for sure. Most of all, it's actually going to pay benefits across the space.
Yeah.
Because the approach we intentionally took was the most general purpose approach. And this is the most painful approach. So just as a general brief, if you look at the space of chips, there are fixed function chips, right? Chips that only do one thing. Right? Like an H.264 media encoder would be one example of this, like a chip that conforms to a standard and does that thing, right? A 5G modem would be another example of this, right? Something that conforms to the standard set by like some symposium somewhere, and this is it, right? And then the next kind of stage of chip design is you might make something that's narrowly programmable, right? Like you might make an instruction set that has 4 instructions, right? And really every chip has an instruction set. For some chips, it's turn on, turn off, and reset. That's it. Right? All you can do is turn it on, turn it off, right? That's a fixed function chip. For some chips, like x86 CPUs, it's incredibly rich, right? You have an instruction for everything. You have these really long, abstruse instructions, even ones with very little documentation that do this one very specific thing. And then you have chips in between, like GPUs that do a pretty wide array of things, right? Like maybe not as much as x86, but like a pretty wide array. And then they do it massively in parallel. And the complexity of designing a chip increases as you go down the spectrum.
Interesting.
Like the spectrum is basically how rich is your instruction set and how rich is the variety of workloads that you're targeting. Right? And the way you do this is a discipline called hardware software co-design. And the way that works is you make what's called a transaction level model first. Right? You have to model like the rough data flows of the chip and, you know, how much bandwidth is going to be required and like things like that. And you have to profile every single workload along these lines. Then the next thing you do is make an instruction accurate model, right? So that's where like you break down the workload into actual instructions. And this is where you're like, we need way more instructions than NVIDIA to do the same thing. We better be smarter about these instructions. Oh, now we have way fewer. So we have a chance of accelerating. Right? This is where like it's really rough, right? Then you go down from that into a cycle accurate model. And this is basically how many cycles exactly is it going to take for my chip to do this? And then you go from there to like actual backend design. And you're like, okay, when I synthesize, this is my gate count. This is how many cores I can have. And because I have this many cores running at this rough frequency, and I can actually hit that frequency at realistic temperatures and on this process node, and when I actually do the whole analysis, my chip should get this performance. And so this is a lot of effort.
It is.
And the effort on this exponentially increases with the number of workloads and the number of instructions. And we have a lot of workloads that we targeted, and we have a lot of instructions that we put into the instruction set. And so this process took a long time for us. And then that's not to mention the design verification that goes into this, right? Like you actually have to like verify all of the finite states in this finite state machine, right? Like you have to hit all the states in order to have confidence that your chip actually will work, even if it's put into this edge case. And that is an even bigger effort. In fact, usually there would be more DV engineers than actual chip engineers in a chip company. Like I think NVIDIA has like a 10-to-1 ratio because their architecture is so complex that they need that.
Interesting.
Right. And we did this. And you might ask, why? Like you're paying this general purpose penalty and you're paying it both in dollars and in performance.
Yes.
And this is hellish, right? And the answer to the performance part is you can be clever and you can do some tricks and you can make the performance penalty minimal. But then there's still like the absolute insanity of the dollars and the time that it takes to make a general purpose chip, especially in an era where the market was non-existent at the beginning of the company. And we were just running headlong into this. We didn't make an intermediate step at GPUs. We didn't make an intermediate step at FPGAs. And really we were like, let's say, how do I put this? We were just really degen about making a blank canvas. And the reason for this is that we could have made, let's say, Plonky 2 ASIC, right? Like something that's really dedicated to this, that has the bare minimum of instructions for this particular thing. Or we could have even like baked Poseidon into an instruction or like something like that. We decided not to do that. And because we believe that the ecosystems that have the most configurability will in the end thrive the most. Like we could have had a very viable business model some other way. We chose to do the more painful thing because it was better for the space. And what's better for the space in the long run is better for us. And this is the same approach that NVIDIA took. So actually in the early days, graphics cards were once upon a time just ASICs for graphics. Most people don't know this, but companies like 3DFX and Silicon Graphics, they would make fixed function shader pipelines for just like tessellating triangles, and that's all it is.
Really?
And NVIDIA was the company that really pioneered the concept of a general purpose graphics chip. And the way they did this is instead of just make a bunch of fixed function shaders that were really good at computer geometry, right? They decided to basically make a very reduced function CPU, but with way more cores. And that's basically what they turned the GPU industry into. It was a non-default outcome. And at first, Wall Street really punished them for it. They actually paid this like big performance penalty, paid a giant verification penalty. They paid this giant software integration. It was like terrible. And by investing in that again and again, that's how AI happened in the first place. AI could not have happened with those fixed function shader pipelines. And we even have deep learning today because they made this degen bet that one day there will be some HPC use case that they did not know. They thought it might be molecular dynamics. They thought it might be oil and gas. Like it could be anything, right? So they made this degen bet and they sunk billions and Wall Street punished them. And they had middling stock performance for the entire 2000s. And then they came out the other end and it was like, oh, there's this thing that you can do when compute gets this big. Honestly, the thing I'm most excited about is you have ZKs, sure. I'm excited to see what happens when you just make a giant amount of integer compute available to people. And I think we don't know the answer to that.
That's fascinating. I think that the nature of performance trade-offs between generality and specific implementations is universal in computer science. And we see this between circuits and ZKVMs. We see this between fixed function chips and general purpose chips. But I think we can see directionally that as you bring down the performance trade-off and you start closing that gap through effective engineering on top of general purpose infrastructure, you're able to have much more expressive primitives that don't have as high of a performance trade-off.
Right.
And I think directionally, those architectures are always the most interesting because the upside of those is substantially higher, both in terms of what they can do in the world and obviously the number of people who can utilize them, the businesses that can utilize them. But one of the things I also want to highlight, and this is one of the things I really liked about Fabric, is we're not talking about a chip that's coming out in 2030. This is not a beta bet on the beam chain. You're in the process of a tape out now of the first chip that already has performance numbers that are much higher than GPU. What does that look like? Where are we? When will these chips be making an impact in the space?
These chips will be out in a couple of months. And production ramp is a process. I don't want to raise everyone's expectations that day one it's going to be like, not like that. But the chips will hit the market, let's say, and people can use them in a couple of months, I think, in the next half year.
That's fascinating.
And so right now we're in the middle of tape out, and we're going to have another 4 weeks in it and then tape out. And then there's 2 months in the fab. And then after that, there's like a packaging and test and bring up process. So you should see chips turning on relatively soon. And then our phones will be ringing off the hook.
I know, right? Tell them an hour up there.
Thanks, Ismael.
Awesome. Want me to lead us back in with the question, or do you want to jump back in?
Go ahead.
Okay. So the question was about, one of the things I've really liked about Fabric is that not only is this directionally a very interesting idea of having these general purpose cryptography accelerating chips, but we're not talking about a vision that's going to be realized only in 2030, right? This is not a beta bet on beam chain, right? These chips are going to be in production soon. You're doing tape out right now, correct? I'd love to know a little bit more about this.
Yeah, sure. Basically, the process of chip design starts with concept and architecture, and then like you basically code up the chip in something called RTL, and this is a very long process. And then basically once the RTL is frozen, you're going to do what's called backend design. So that's where you actually turn the Verilog RTL that you created into a bunch of rectangles, billions of rectangles that you send to TSMC and they build it, right? We are in the mid to late stage of backend, and that means that we're like a couple weeks, like 4 weeks away from tape out. And basically the moment that happens, you send this like terabyte sized file to TSMC. You actually sit in a room and upload it over FTP, fun fact. And it's a very long upload. So you're just like, they give you boba and
I love that.
Sit in there. Anyways, that ordeal is about to happen. And then it's 2 months in the fab and then it comes out. And from that point on, it's a little bit of a random variable how long bring up takes. It could be 1 week, it could be 6 months. But we should our expectation is that we start seeing chips actually start to hit the market at that point and be able to turn on and do something meaningful and show something basically to the world.
I'm excited. I think it's going to blow people's minds when they start seeing the performance of these. And so I want to move up a couple layers in the stack. Because what I think is also underappreciated about hardware companies is that you are not simply building a chip. You're building everything from a compiler to libraries to interface with the chip, all the way up to co-designing proving systems to interface more efficiently with the libraries that interact with the chip. And what does it look like for some of the co-design you're doing with backends right now? I've seen announcements over Baby Bear, Goldilocks, Mersenne 31, a lot of Stark-based backends you guys have started with.
That's right.
And so what does that look like? Where are we? What do you expect the performance to be?
On all of those?
So if you were to look at a Fabric VPU versus a GPU on those proving backends, what do you think the marginal improvement will be?
So on the NVIDIA 4090, we did a benchmark for RISC-0 that I think is very indicative. We took their hardest, most heterogeneous part, which is eval check. Eval check is basically like what happens when you actually arithmetize the circuit and actually run the constraint checking on the GPU. And so it's just a bunch of random modular arithmetic instructions. It has no rhyme or reason to it. And so in some sense, it's the hardest to run on dedicated hardware, right? And so we took that and compiled it, and it was like 5x the 4090.
Oh, wow.
About 11x the 3090. And what's really notable is we're fighting this with our hands tied behind our back.
Yes.
We have half the logic area of the NVIDIA 4090. We have, and not only that, but they're on 5 nanometer.
Yep.
And 5 nanometer has literally 5 times the transistor density that we have on 12 nanometer. So they get 5 times the transistors per area.
Yeah.
They have twice the area, so that's 10x. And they run at a 2 times higher, actually more than 2 times higher clock frequency. They run at a 2.5x clock frequency. So that's a 25x advantage that they have. And because they have armies of people, they can do full custom design. So they can go in, like, customize every standard cell and, like, actually design at transistor level. And they don't have to spend more time because they just have an army of people.
Yes.
Right. And so they actually have, like, about 50% higher utilization efficiency on the metal wires. There are just giant blank spots in our chip because we didn't have time to go and optimize those little things. That is a 40x net advantage that they have. We beat them by 5x. That's actually, the architecture is like 200x.
Yeah.
And then it's a 5x because we're a startup and we're releasing our first product.
Exactly.
That 200x is what you can expect to see over the coming years, and it's what we intend to deliver.
I love that. And I love the approach that you guys have taken as well. I think a lot of companies that have these fundamental R&D components tend to overbake.
Yeah.
And they hold on to the vision of what they want to build, and they can't actually take a meaningful step there because they don't want that step to not be correctly reflective of the long-term outcome they're hoping for.
Yes.
They don't want to be
100%.
5x.
Yes,
they think they can
yes.
be 200x in a few years.
100%. And I expect the critics will come out once our architecture is, like, super publicized. And they'll be like, I would have done that. And I would have done that. And I would have too. If I had more time, there are a number of things that I would have done. And those things inherently cost time, inherently cost money, inherently cost design verification cycles.
Yeah.
This is the thing that most people don't realize about CPU design, which this is a subfield of, is that CPU design requires these iteration cycles that end in, like, exhaustive verification of everything you're doing. And so when you bake in a feature, like, let's say that you have something like caching and you have prefect.
Yes.
Or let's say that you have something like speculative execution, or let's say that you have a superscalar architecture, or all of these modern CPU concepts that are obvious that, like, everyone should do.
Yeah.
Every single one of those exponentially explodes the number of states in your finite state machine, and therefore explodes the cost of verifying and taping out the chip. And we went with this radically simple architecture.
Yeah.
And in a couple of years, we're going to look back and we're going to be like, wow, that architecture. Oh my God. But that is the pragmatism that has enabled us to ship this so fast.
Yes.
There you go.
I love that. And I also think that the way that you made a bet on verifiability is very prescient to what we're seeing now in the space. If we look at crypto very broadly, like, we see these trends that start with a very small group of people in the space talking about an exciting new idea, and then it becomes intertwined into the zeitgeist of what everyone is going to build on and do.
Yes.
And we've seen ZK become this.
Yeah.
Several years ago, I like to tell the story that I was in San Francisco and I was starting Lagrange, and I was at a crypto event. I was listening to a talk.
Yeah.
And the speaker said that in a couple of years, every app was going to be a cross-chain.
Wow.
And it was like a bold prediction at the time, like this idea that you'd have something on Polkadot.
That's spicy at that time.
It was very spicy, but the idea that you'd have something on Polkadot composed with something on Cardano was a little fanciful. But in reality, it turned out to be very correct. I can't think of a DEX now that doesn't support a wrapped asset. And I can't think of very many protocols that don't have cross-chain deployments. But where we are right now, we see a similar thing with ZK.
Yeah.
I wouldn't anticipate that in 2 years, many rollups would not be using ZK for at least fraud proofs.
Yeah.
Likely for validity proofs as well when we bring down cost of proving by 1
Within 2 years, it's just going to be all validity.
It will.
In my opinion.
It will.
Yes.
It will. You're going to move to validity-based interop. You're going to move to execution extension through coprocessors. You're going to move to verifiable data, ideally through ZK TLS or some type of additional mechanism to add verifiability to exogenous data. And so you're going to move to everything in crypto being built around zero-knowledge proofs or other forms of cryptography at the core. FHE for private shared state.
Yes.
TEs for cryptomatons.
Yes.
Which is something I learned from you the other day. But yeah, that's why I think it's so exciting, the way that you guys have bet on that before the broader market has anticipated it.
Yeah. This is the thing about being a hardware guy is you have to be almost a little bit degen.
Yeah.
And this is a necessity.
Yes.
Because if you do the standard lean startup thing.
Yes.
And let's say you validate your product and all that, and there's market demand, now you build it. Right. That is not going to happen in time because there's some other degen who probably did it like 6 months earlier than you.
Exactly.
Because they saw the glimmer, right?
Yeah.
And so you actually have to do lean startup, but 2 years in advance.
Yes.
Which is not lean startup anymore. Like you're not testing assumptions. You're trying to think very first principles about what's going to cause what, right? What domino is going to knock into what domino and then what it's going to be in 2 years. Because if we start building our Gen 2 today, in 2 years, it's going to come out. And then what are people going to be doing then? I don't even think that I know fully, right? But I have to know. That's my job. And you have to be degen. And that's one of the most fun things about hardware is it's an art of predicting the future, right? And yeah, exactly, basically.
But I think it's interesting because for the uninitiated, they wouldn't think of hardware as an agile industry. They would think of it as very much this staid manufacturing, supply chain oriented industry. And this is why I think the more that the broader crypto and the broader cryptography space is exposed to the practices of what goes into developing a general purpose chip here for cryptography, the more confidence there can be in the space that this is directionally the right outcome.
Yeah.
Like
I'll be spicy here and actually say it very much is a state industry. We are the only people who are insane enough to be doing the agile hardware thing because agile hardware is an oxymoron.
Yeah.
You should not do this. If you're trying to optimize the EV of a company, you should not do this.
Yeah.
We are doing it because we believe in the crypto space. We want to accelerate it. And we're crypto native. And what it has meant is that as the space changes and moves and weaves in and out of various narratives, we end up having to change our product. In fact, there was a very late cycle change to our instruction set about 3 months ago.
Yeah.
We rewrote the entire instruction set in 3 months, and now it's headed for tape out. And now it's going to be 3 years. Like it's going to be proof for the next 3 years, let's say. And that's the kind of agility that a real crypto hardware company needs.
Yes.
There was an ASIC that came out a while ago for MSM. And now, like, what are they going to do, right? Like, so I feel sad for them because they did what normal chip people would actually recommend do. You see the same thing in AI, actually.
Yeah.
A lot of people made convolutional neural net ASICs that just went away when LLMs came out and became the dominant narrative. And that's really unfortunate too.
Yeah.
And so in the hardware industry, you have to be able to adapt to this, but it's not for everyone. Like, in fact, we've had people be very frustrated on our team with the speed with which we have to leave in and out of things.
It's the problem with building for a specific embodiment of a product in a very quickly changing market.
Yes. And the people who have stuck it out on our team have been the people who can say, I'm going to rewrite the RTL in a few weeks. I'm going to do that. And they have been able to do that, pulling all-nighters.
Yeah.
They've been able to do what takes other teams months. And the same thing would have taken Intel 9 months.
Yeah.
And so they just would have never done it. They would have released this product and they would have just slowly made the next.
But that's the advantage that you have as an early stage company.
Exactly.
Much faster, much more nimble. But a lot of people make mistakes. They use that speed and they make missteps in building things that are too specific for a market that might not exist.
Exactly.
And so that's why I think the approach you guys took is, I think we're seeing it substantiated.
Yes.
And one of the things I also want to touch on here, because you have a very interesting perspective on this, the recognition of crypto as a significant international industry. We've seen in the most recent election in the US, a lot of conversation and recognition over crypto. And you would be the first company producing a chip in TSMC that is not just an extractive Bitcoin miner. It's a chip that will accelerate cryptography that's hopefully accretive to the space.
Yes.
What is the recognition like of crypto within TSMC?
So funnily enough, this is not a TSMC story, but this is rather Synopsys.
Yeah.
Who we're very excited to partner with for our next generation chip over the EDA tools that are necessary to license. And the SVP there, his son actually works at Wormhole.
Really? I love that.
Yeah, that actually helped a lot.
Yeah.
It's through chance things like that actually we've been able to pry open the hardware industry and open their minds.
Yeah.
But on the TSMC side, there's a fun anecdote I have. I think this is not under NDA, but my very first call with TSMC, we were discussing like, okay, why is this product even a thing? And I was like, you guys have a fab, right? I went on a limb because I'd never done this customer discovery with them. And they were like, yeah. And then I was like, you have fab machines? They're like, yeah. And then I'm like, these fab machines go down sometimes. Yes. And then I'm like, what happens when those machines go down? We lose billions of dollars per day, right? These fabs are like cash cows, right?
Exactly.
Like you lose billions of dollars per day. I'm like, what do you do to diagnose those fab machines? Because you can't send your proprietary data to ASML, can you? And they were like, yeah, I guess we can't. So they fly someone out. I'm like, how long is that guy on the plane to Taipei? And they're like, oh, wow, quite a bit of time. And then I'm like, yeah, during that time, you lost how much money, right?
Yeah.
What we're accelerating is this thing called programmable cryptography. And it can solve this problem for you because that guy could remotely diagnose your machine without looking at the data.
Interesting.
And this was like, for them, that was like the eye-opening exercise that they went through.
But it's a recognition of something tangible.
It's a recognition of something tangible. And it's actually like more fundamental than that. I think like everyone in the world, we live in an age of discord. We live in an age of war, discord, disbelief in authorities, disbelief in the financial system, disbelief in governments, disbelief in systems and institutions, right? And this disbelief makes everyone want to trust again, right? Like they want to believe, but there's so little grounds to. There's no good reason that someone has to believe in anything. And so there's this entrenched cynicism on one hand, but there's also this desire and hope for something better, right? That is deep within everyone. And I think that's what we saw with a lot of folks in hardware is like, if you have them see that they actually want this for society. And you see how programmable cryptography can change the equation, not in blockchain, not in crypto, but in trust in general, right? They're like, oh, wow, this is a really powerful Schelling point for humanity to move towards. And that's ultimately what really is compelling for people.
I think that's very well put. I think if we look at much of the digital world, it's highly adversarial.
Yes.
The number of places that will take your data, that will sell your data, the amount of time it takes to safeguard yourself, your accounts, your passwords, your identity, every component of your life as you interact online puts people in a space where they have to be continually cognizant of whether or not the things they're interacting with are predatory towards them. And it is not a way that we have historically seen productive, high-trust societies operate. It's this new embodiment of this highly selfish online kind of digital world where everyone is out to get you. And we see this in crypto too, right? A single mistake on not checking what your ledger is signing can take all of your assets. And so this is why I think the fundamental aspect of blockchains that's interesting is establishing a root of trust around a state machine that is updated across a clear set of logic under which no single actor can deviate from. And I think that a lot of cryptography can take that concept of this decentralized root of trust and extend the expressivity of what you can do with it. To be able to have more things that root on the consensus of a chain.
Absolutely.
And so as a final take here today, I'd love to know where you see the space moving over the next 2 years. If you think of where Fabric is and where crypto is 2 years from today, we're sitting here at DevCon in 2 years. What does it look like and what are we talking about?
I think we will see mainstream adoption within 2 years for use cases that crypto has been unable to actually satisfy in the last 10 years.
Interesting.
And this is like the really exciting thing. This is the thing that lets me get out of bed in the morning and run a hardware company. Is things like zk-TLS that are bringing Web 2 to Web 3. And things like these cryptomata that people are talking about that reside within TEEs. And it is not just a flash in the pan. It's not just another fad. It's not just another narrative. It is sending songs to the Billboard 100. It is letting people take payday loans at lower interest rates, right? These are not a joke. Like these are going into the real world. I saw even someone I know was building this thing that allows people to underwrite mortgages with zk-TLS on chain. And I was like, oh, and they want to make the underwriting process like a couple minutes, right?
Fascinating.
And things like this, and you're like, huh, like it's really starting to, and I don't know which one of these apps is going to work and it's not going to work, but the wall between Web3 and Web2 is being torn down as we speak.
Yes.
And when that wall crumbles, you're going to see a Cambrian explosion of applications, the likes of which we've never seen before. You're going to see actually Web3 not become, yes, yet another buzzword, right? People have been saying Web3 for years.
Yes, they have.
You're going to see Web3 become a reality the way Web2 is a default reality now.
Yeah.
And that is what I'm excited for. I'm excited to see what happens when you actually connect Web2 to Web3. All the credit, all the insurance, all the supply chains, all that stuff.
Yes.
We're going to see what happens when people are able to programmably create smart contracts on those substrates.
I love that. I think the part of that perspective that's the most interesting is bridging between Web 2 and Web 3, using things like TEEs and ZK-TLS to try to get more types of exogenous data on-chain and to try to allow on-chain state to interact with off-chain actors. And I think that really opens up what blockchains can access and what we can build. And so I think that's a phenomenal place for us to leave off here today. Thank you for being here, Michael. Thank you for joining this conversation, and hopefully at another conference we can do this again soon.
Thank you for hosting.